In this video, we're going to learn about solubility equilibria. So there's a term Ksp. This is the equilibrium constant for a dissolution reaction. And frankly, it's no different from a classic KEQ, regular equilibrium constant. Um, Now, in a saturated solution, Q is always going to be equal to Ksp. And if a solution hasn't quite reached its maximum amount of concentration, it will be unsaturated, and the Q will be somewhat less than Ksp. So if we look at, say, lithium fluoride, at 25 degrees Celsius, its Ksp is going to be 3.8 times 10 to the negative third. And that's calculated via this. Here we have the equilibrium equation. So we have lithium fluoride in the solid phase equals lithium ions and fluoride ions that are aqueous. And the K expression for that is going to be equal to concentrations of products over reactants, except, wait a minute, the reactant is a solid, so it's omitted. So we just have the concentration of lithium at equilibrium times the concentration of fluoride at equilibrium, and apparently that's equal to 3.8 times 10 to the negative third. So the 0.062, that is the molarity of lithium ions, and that's also equal to the concentration of fluoride ions. We can say that x squared is equal to 3.8 times 10 to the negative third because we're going to say that lithium is x and fluoride concentration is also x, since they are 1-to-1 in this solution. So we get x squared is 3.8 times 10 to the negative third, and x would be 0.062, and that is a molar concentration at equilibrium. So again, in a saturated solution, we're at the point that absolutely no more solute can dissolve. But if we're in an unsaturated solution, we could keep on adding some lithium fluoride and dissolving it before this equilibrium is established. So in this case, right, lithium fluoride concentration, which happens to also be equal to lithium concentration and fluoride concentration, we get that from the fact that this is a 1-to-1-to-1 equation. If the concentration of lithium fluoride is 0.062 molar, then the solution is saturated. However, if the solution's concentration is less than 0.062 molar, then the solution is unsaturated, and you could still keep on dissolving some more lithium fluoride. Let's work through some practice problems, like calculating the Ksp for lead 2 chloride if 1.00 liters of a saturated solution of lead 2 chloride is found to contain 4.41 grams of lead 2 chloride that are dissolved. So what we can first do is convert this number of moles of lead 2 chloride, number of grams into moles. The molar mass of lead 2 chloride we already have out is 278.1 grams per mole. So this comes out to a concentration of lead 2 chloride that is 0.0159 molar. Next, we need to look at the equilibrium expression. And for this, I'm actually going to make an ice table. This means that we have initial concentrations, change in concentration, and what the concentration is at equilibrium. Initially, our concentration of lead 2 chloride is nothing. We can just completely ignore this because this is a solid. So ignore all of this, right? But we can say that initially, before any lead 2 chloride has dissolved, there is a 0 molar concentration of lead 2, and there's a 0 molar concentration of chloride. But when we dissolve the lead 2 chloride, we can increase the concentration of lead 2 by positive 0.0159 molar, because we know that at equilibrium, at that saturation point, the concentration of lead 2 chloride is this, and this is 1-to-1 with the lead 2 chloride. So we know that lead 2 chloride is 1-to-1 with lead 2. So if the lead 2 chloride is 0.0159 molar, then the lead-2 needs to also be 0.159 molar. However, important thing here is we have 2 chloride ions that are formed per lead-2 chloride. We can almost look at it like a stoichiometry problem. If we have PbCl2 that is at 0.0159 molar, what we can say is that there are 2 molar concentration of Cl minus per every 1 molar concentration of PbCl2. And that's how we get to this equilibrium concentration. Sorry, this is laggy. Of 0.0318 molar. We're just multiplying this by 2 to get the molarity of chloride at equilibrium. So bottom line is we start off with no lead-2 chloride dissolved, and at the end of it, once we've reached the saturation point, our concentration of lead-2 is this, and our concentration of Cl- is this, which allows us to use the equilibrium expression. We know that Ksp is going to be equal to the concentration of lead-2 times the concentration of chloride squared. Again, there is no denominator to put in because we've got a solid, and that's always going to be the case with a Ksp. You never have to worry about the reactant side because it's always going to be solid. So if we plug in the numbers, the concentration of lead-2 times the concentration of chloride squared gives us a Ksp of 1.61 times 10 to the negative fifth. Finally, I have another problem that is calculating the aqueous solubility, and we're going to make this a molar solubility first before we go into a grams per liter solubility of Ca3PO42. We need to know the Ksp at the temperature that this is happening, and that apparently is equal to 2.07 times 10 to the negative 33rd. So the first thing we need to do is write out our equilibrium equation and note that since this is Ca3, we put a 3 in front of the calcium. And since this is PO4 we need to put a 2 out in front of the phosphate. And in this case, we're going to need to use another ice table. What we'll do is we'll say that initially there is 0 concentration of calcium phosphate. This is something to ignore because we're dealing with a solid here, so we can ignore it. But our calcium ions initially, before we dissolve any, there are none, and our phosphate ions, there are none. But what we'll say is that the calcium ions increase by a factor of 3x. We don't know how much. And we don't know exactly how much the phosphate is going to increase by just yet. What we do know is that it's going to increase by 2x. And the 2 is because of the coefficient of 2, and the 3 here is because of the coefficient of 3. And of course, at equilibrium, we just have concentrations of 3x and 2x for our calcium ions and phosphate ions, respectively. So next we can use our Ksp expression. This is equal to calcium concentration cubed times phosphate concentration squared. The squared has to do with the coefficient of 2. The cubed has to do with the coefficient of 3 from the equation. Next, what we'll do is we will basically say that Ksp, which was given to us before, it's this, Ksp, is equal to x, sorry, it's going to be 3x, and we'll cube it. And then we're going to take the, the 2x and we'll square it. 3x cubed times 2x squared gives us 108x to the fifth. Check that if you need. We can divide both sides by 108 and get 1.92 times 10 to the negative 35th equals x to the fifth. Take the fifth root of both sides, and we find that x is equal to 1.14 times 10 to the negative 7th molar. Now, interestingly enough, that 1.14 times 10 to the negative 7th molar being x is just the concentration of aqueous calcium phosphate. And so what we can say is that if this is the concentration of Ca3 PO42 aqueous, sorry, that's a 2 there. If we can say that, then we can multiply this, because we actually have at this point the molarity of saturated calcium phosphate is this many moles per liter. But if we need to convert this into a grams per mole, or sorry, a grams per liter concentration, we can just multiply by the molar mass, and the moles cancel, and what we end up with is 310.18 times 1.14 times 10 to the negative 7th, which is equal to 3.54 times 10 to the negative 5th grams per liter. That's a negative 5th. There we go. All right, so that's all for KSP. Hope this video has been helpful. Feel free to leave any questions or comments in the comment section below. Thanks for watching.